Alright, hey guys, what's going on? So today we're going to be talking about the meaning of the Klein-Gordon equation and the Klein-Gordon solution. So for a while now, we've sort of gone down the rabbit hole of looking at the Hamiltonian, specifically for the Klein-Gordon equation. We've also have been looking at the dynamics that come from this Hamiltonian and that come from understanding the Klein-Gordon equation sort of within the context of really just the Hamiltonian, the spatial Hamiltonian, and understanding the 0-point energy of the spatial Hamiltonian. We're going to come back now. We're going to step back, and we're really going to take a look at what the Klein-Gordon equation can give us, what the solutions mean to us, is what we're kind of looking at here. We really want to understand what the solutions actually mean, and so it's going to help us understand a little something about why we hear in popular videos, perhaps espoused by Neil deGrasse Tyson or Brian Greene, telling us that time and space essentially is fuzzy. Right? We're going to understand exactly why that is the case today. Right? And this is going to come out of understanding what the meaning of the Klein-Gordon equations are, or the Klein-Gordon solution is. Okay, so let's get right into this. And before actually we get into this, make sure to hit that like and subscribe button. And now let's get into it. So we're going over the meaning of the Klein-Gordon solution, and what I've outlined here is really just a rote derivation of how this goes, right? So we're going to start off by saying that the solution is an operator. The solution to the Klein-Gordon Lagrangian, if you will, or the Klein-Gordon equation, right? If you recall, the Klein-Gordon equation was an oscillatory equation in time and space. It had temporal components and it had spatial components. And we recall that the Klein-Gordon solution, right, was this right here. Right, so this is an operator. We're typically introduced to the solution as really just a solution to the equation. It's an integral over our spatial momenta, and this is typically how we're presented this, but we will always want to keep in the back of our minds that the solution to the equation is an operator that acts on states, right? So if we take a look here, so our solution as a function of spatial coordinates acting on something that contains 0 particles. This is a state that contains 0 particles, right? So we could sort of think of this as the temporal, right here, this is sort of like the temporal, not the temporal, but sort of, this is the operator, or the solution, right? And this is the thing that contains the particle number, okay? So particle number. So, and every time we operate on the state that describes the particle number, what we get is a particle number, right? So that's one particle at a particular location, right? So the location again is given to us by this operator, and the particle number is given to us by the state that we're acting on. So intuitively, we're recalling, perhaps not intuitively, nothing about quantum field theory is intuitive, but we want to recall the solution, which looks like this, and we're operating again on our 0 particle state, and then when we act on our 0 particle state, we can really condense this, right? Because if we can FOIL this out, right? So we take this here, act on it here, and we act with this guy too. This, however, is going to go to 0, right? Because this is an annihilation acting on a 0 particle state, right? So if you annihilate 0 particles, that's just 0, right? So this part here is going to go away, okay? And what we're left with is this guy right here, okay? And then if we act on the part of the state with this, then we get a particle, right? But this is a particle with momentum, not in a particular location. This is a particle with particular momentum, okay? And so that gives us one particle with this momentum. And then what we do is we say that, okay, so it's been reduced now to this. We're getting closer to something that looks like a shorter equation, right? And we just keep it like that for right now. So this is basically the same thing up here, but now we're bringing this down here, right? We brought this all the way down here. So this always stays true, or not stays true, but this is carried down. And what we see here is that one particle at a certain position is a summation over multiple momenta of a particle with that momentum. So what is this telling us? This is a weird thing, right? And I want to spend a little bit of time on this because this sort of helped things click for me as well. When we look at this equation, we are summing over multiple momenta, essentially an infinite number of momentum states. So this is one particle that has multiple momenta, right, at a certain position. Well, this is very, very sort of indicative of the Heisenberg uncertainty principle, right? You cannot know a particle's position without smearing out or without having some ambiguity with it of the momentum of that particle, right? So if we want to know what the position of that particle is, if we want to know exactly what position of the particle, we need to understand the particle in terms of multiple momentum states. And there's really no way of going about that. That's the Heisenberg uncertainty principle. That's the principle, again, that we can only be arbitrarily close. We can only be arbitrarily close to position, knowing a position of a particle, but that comes at a cost of summing over multiple momentum states, right? So what does this look like? This, again, so we have E, so we essentially are summing over multiple momentum states, and when we do that, we get this factor here, right? But I'm omitting that, and we're taking a look here. We have this exponential multiplied by the state, one particle state, the second exponential multiplied by single particle state. Okay. And you can imagine as we increase momentum states, right, we just get more and more of these summations. We essentially get an infinite summation state unless we have some bounds here, right? Unless we have a bounds here. I don't want to put a 0 here. What I mean to write is some lower boundary and some upper boundary of momentum states. We could do that. But if we don't, we have an infinite number. Okay? Now, each field excitation, again, so this is essentially what this is saying, is that each field excitation is a weighted sum of momentum states. That is sort of how we view this, right? Let's take a pictorial understanding of what this might look like. So here's our space, right? So suppose that So this is our space. We have X, Y. Actually, I'll do it like this. We could view this as sort of X, Y, and Z positions. This is sort of a little bit getting into some general relativity picture, but I don't really want to confuse this like that. But essentially what we have is a position, right? So we have a position right here that can be described by X, Y, Z, and a T coordinate. So we can specify that point, but when we specify that point, we have a summation over states here, over certain momentum states. And again, the momentum states can be described by the frequency at which the particle is moving, right? So that's that, right? So if we have a particle and we want to know exactly what its position is, unfortunately that comes at the cost of summing over multiple momentum states. And the same goes for the alternative. If we want to know, and we could do this calculation, if we want to know what the what exact momentum is at within some particular bound of space, we therefore have to sum over multiple spatial values, if you will, and that sort of encompasses a volume in space, right? So if we want to know the momentum, then we have to sum over multiple position states, right? And multiple position states, that encompasses a small volume. So everything comes at a cost. So I mentioned how this sort of explains sort of the unintuitive fuzziness of space-time that we often hear from people like Brian Greene or Neil deGrasse Tyson, this idea that space is fundamentally fuzzy at the quantum level. The way I like to think of this is through this example, because the fuzziness really comes from not understanding what exactly the momentum is at a particular location, or not exactly knowing what the position is at a location. That's exactly where the fuzziness comes from. So, and that we could see that in this example. Okay. Now I am quite proud of myself, and I think I know I'm quite proud of you guys for sticking with me on this. I know it's been a while. I know that there's been some gaps in me uploading these videos. I think the next video is going to be video number 40, right? So that we've come a long way. This is exciting, and I'm going to continue going down the road until we finish with this book, right? This book, again, is No Nonsense Quantum Field Theory, and when we're done with this book, then I'm going to move on to the next book, and I'm going to try to pick up the speed here, because I know you guys are anxious to know what book is going to come next. So with that being said, I will see you guys in the next one. Bye.